All right, here we go. So I'm going to draw pictures for these theorems. It says if two lines are parallel to the same line, then they are parallel to each other. So that was the one that showed up on that quiz, an example of the transitive property here. So we've got, if we have line A is parallel to line B, and line B is parallel to line C, then A is parallel to C. Then theorem 3.9, in a plane if two lines are perpendicular to the same line, so you have one line here, call it A. If two lines, let's call them B and C, are perpendicular to the same line, then they're parallel to each other. We use that in squaring off things in like construction. That'd be like a door frame or something to look like that. And then in a plane, if two lines are perpendicular to one or two parallel lines, so here we have two parallel lines, call it A and B. It says if in a plane, if two lines are perpendicular to one or two parallel lines, then it is also perpendicular to the other. Something like that. So if in a plane, if two lines are perpendicular to one of two parallel lines, so it could be perpendicular to either one of these, then it is also perpendicular to the other. Yeah. And then we're going to use the idea of perpendicular lines to get complementary angles to set up equations here, so, or vertical angles in this case. So in A, we've got this perpendicular symbol here that means 90 degrees. Because that's a vertical angle with x squared plus 9, we have x squared plus 9 has to equal 90 degrees, and then solve it. Now this one, when we solve it, subtract 9 from each side, I get x squared equals 81. We've got to take the plus or minus square root of each side. And so we got square root of x squared equals plus or minus square root of 81. So x equals plus or minus 9. And both the positive and negative will work in this case. Sometimes in geometry we toss out the negative value because it would produce a negative measure for the angle of side length. That's not happening here. So the negative 9 here works just fine. So x equals plus or minus 9 will force that to be perpendicular right there. In part B, what would x have to be to force those two lines to be perpendicular to each other and make a 90? Well, yeah, you can probably do it in your head. X plus 62 has to equal 90. Subtract 62 from 90, which is what you're doing in your head. You get x equals 28 degrees. So if x is 28 degrees, that'll make a 90. It'll be complementary to the 62, and thus make a 90. Right. A lot of what they do in Common Core is like using a little bit of geometry and a whole lot of algebra. It's an example of that. So it's an integration of the two. So we're going to use geometric definitions to write an equation, and then the equation we have to solve goes back to the end of your last packet, that's solving by elimination. That would be my hint in this. We're going to actually create a couple of different equations. One of the equations by geometry would be 2y plus 5x plus 10 equals 180, because those two angles are supplementary. So 5x plus 10 plus 2y equals 180. Now that's a problem because there are two variables in one equation. If you have two different variables, you need two equations to solve it by substitution or elimination. So here's the other relationship they give us. They tell us that 3x minus 10 plus 3y minus 20 has to equal 90. What's the question?
Is it okay because it does more?
That's fine. All right. My hint here is use elimination. So what we're going to do is combine some like terms here, or move some things over. I'm going to subtract 10 from each side. And that creates a new equation, 5x plus 2y equals 170. So just move that 10 over, subtract it from each side. Here I'm going to combine like some like terms first. So I'm going to take the negative 10 and the negative 20, write this as 3x plus 3y minus 30 equals 90. And then add 30 to each side. So my new equation here is 3x plus 3y equals 120. So those are my two equations, and I wrote them in what's called standard form, ax plus by form, so that I can line them up and use elimination on it. So hopefully this looks familiar when I move them together like this. Does that look like something we've done before? System of linear equations with two unknowns. This is the end of chapter 2, that last page in there we're reviewing. Of course, we made problems that forced this to happen, but it's just a way to practice our algebra. So what do you guys think would be the easiest variable to eliminate here? Which one would you eliminate? I don't know if there is the y. I would say the y too. I don't think one is easier than the other, but the y has a lower common multiple. What's the lowest common or least common multiple between 2 and 3? 6. So I'm going to multiply the first equation here by 3 on each side. And I'm going to multiply the second equation by, how about negative 2 on each side? You see why I'm using negative 2? I want to get a negative 6y right here. Negative 6y, and then a positive 6y up here, so that when I add the two equations, they cancel out. So that's the idea. So my new equations are 15x plus 6y equals 510, I think.
Yeah.
Okay, and then negative 6x minus 6y equals negative 240. So I'm just distributing that 3 across the top and the negative 2 through the second equation to create two equations, put a line underneath it. What I'm doing is adding these two. I've got 9x, the y's are eliminated, hence the names. And then 510 minus 240 is 270. And then if I divide by 9 on each side, I've got x equals 30. And we've got a kind of higher level problem solving sort of question here. They didn't say just find x and plug it in and get the measures of all the angles, which is what we've been doing a lot of times. We get x, then we just go plug it in and get the measures of the angles. This time they ask us, which angle of all the angles in both those pictures is the smallest? Can you tell me why? Let's see. So we've got x equals 30. We've got x equals 30. Got that? I give you a ton of room down there. This is real small. So x equals 30, and we're going to go up here and just test it. Let's see. Let's see what happens here. So if I plug in 30 right here for x, it's going to go in right there. 3 times 30 is 90. 90 minus 10 would be 80 degrees. That gives me 80 degrees here, which would mean this angle right here, because this is perpendicular, would have to be 10 degrees, right? I don't actually have to find y, because I'm using geometry and the idea of complementary angles there. So that's 10. I think that might be the smallest line. So if that's the y you're referring to, you're right. That's 10 degrees. Over here, if I put 30 in right here, 5 times 30 is 150 plus 10, I get 160. So that would mean this angle is 20 degrees. So the 10 degree angle is the smallest angle. 10 degrees is the smallest angle between these 4 angles that are labeled. As you go through this unit, you'll run into some problems where you have to do more algebra than geometry. The geometry is like just the first step. We'll have quite a bit of that in here. All right. application or two here. Suppose you plan to install molding on the sides and top of a doorway, or even if you're doing molding along the bottom here, like the floor here, this black molding, you have to do some special cuts here. You cut the ends of the top piece and one end of the side pieces at 45 degrees as shown. Will the side pieces of the molding be parallel? So will these be parallel if you cut 45s here and here? So if I move that in right there, it's not the best, but so I've got 45s right here and here, and those two 45s are going to make that 90, right? Same thing over here. This is why we got 45. So 90 over there. Does that look kind of like one of the pictures for the theorems in the very beginning? That's the first one we did. Okay. So if those two are 90s, if you cut 45s, put them together in that way, then you're guaranteed that these two sides here and here will be parallel, like the sides of the door, the little door frame. So will the side pieces of molding be parallel? Yes. I think that was theorem 3.8. Yes, if two lines are, do you guys know what the symbol is for perpendicular?
Yeah, it's a T, upside down T.
So there it is. We should just use that rather than write it out. We're in math. If two lines are perpendicular to the same line, comma. The only reason I'm writing this out is to say theorem 3.8 is kind of relative to this textbook only. It doesn't really say much. So if two lines are perpendicular to the same line, then they are parallel to each other. And let's use the parallel symbol. Two parallel lines parallel to each other, so that guarantees it. So that's why we do those 45-degree angle cuts there. That's assuming the doorway is square. So there's one application of those theorems. Do a little proof by picture here. See if you can move through all this. There's something like this on your test here, but it says in a plane, it says C is perpendicular to B. So just draw two lines that are perpendicular, label one C and one B. So start with that. Doesn't matter where they cross. So call one C and one B like that. Then it says B is perpendicular to D, so which way will D be going? Yeah, let's see. So somewhere down here, draw in D. If you have to, you can make your line longer if you run out of room. We'll see what happens. Then it says D is perpendicular to A. Yeah, so A is going to go the same way. This is proof by picture. We've got some perpendiculars here. You can just put a little perpendicular marking at one spot. Because these are vertical angles and these are a linear pair, you know they're 90s all the way around. So one little 90-degree marker is all you need, okay, based on our other theorems and definition. So prove C is perpendicular to A. So I'm looking at the picture here. You looking at the same picture I am? Is C perpendicular to A? Here's C, here's A. Proof by picture. So, according to the picture, that's good enough. So.